Hello everyone. I'm Vamsi, a fifth year PhD student at the University of Nebraska-Lincoln, and today I will be talking about combining multi-type data to improve categorical trait prediction. This work was done in collaboration with Dr. Diego Jarquin and my advisor, Dr. Rekha Howard. Traditional plant breeding techniques have led to significant gains in crop yields for several decades. Improvements to crops were made through by using phenotypic and pedigree information. The use of genomic molecular data marker is a relatively new technique to improve breeding strategies. It's well known that most of the traits that have economic importance are controlled by multiple genes. Thus, genomic selection was proposed as a method where the entire genome is used to predict the phenotypic outcome. Genomic selection uses DNA marker data along with phenotypic trait data to build a statistical model in order to make predictions. The model can then be used to predict the phenotypic trait outcome of individuals that have genomic information but do not have any associated phenotypic information. Breeders use these predictions to select individuals that have favorable trait outcome without having to perform field trials. One of the primary concerns with plant breeding programs is the costs involved in phenotyping. On the other hand, genotyping costs are reducing dramatically every year. Thus, genomic selection methods help breeding programs improve predictability while reducing costs. So this is a simple outline of a genomic selection method. Modern plant breeding programs collect several types of data other than genomic information and the main trait information. They collect data on several other secondary traits such as plant height, seed weight, etc. They also collect high-dimensional data such as high-throughput phenotyping, fine-grained weather data, and image data. It is well known that these different data types of variables have an impact on the main trait. So if we can integrate these different types of data with the genomic information, we could potentially improve the prediction accuracy. So the question then is, how do we leverage these different data types to improve prediction? There are several challenges associated with this, which we will discuss in a minute. Another interesting problem is that some of the phenotypic traits of interest are categorical in nature. For example, we have susceptibility to disease, resistance to salinity, resistance to drought, etc. Most of the methods in genomic predictions address a continuous response. So in this work, we develop methods to integrate three different types of data, with namely the secondary trait, the weather covariates, and the genomic data, and we build models for multi-category classification. Let's look at some of the challenges in this work. So the first challenge is an obvious one in any genomic prediction, which is the high-dimensional nature of the genomic data. So let's look at this graphic here for a second. Here we have the categorical response Y. The secondary traits are represented by the purple color, the weather represented by the blue color, and the genomic information represented by the green color. The size of each box here indicates the second challenge, which is that the number of genomic variables are much larger than the other two types. Often genomic variables are in the tens of thousands. On the other hand, weather variables are a few hundred at maximum, and the secondary traits are just in the tens or 20s. So the question then is, how do we build models that are able to access the information present in the three data types of such differing sizes without the genomic data type drowning out all others due to sheer numbers? Another challenge in this problem is that the secondary trait is correlated with the response. But also the secondary trait is affected by the genomic variables and the weather variables. This is a classic case of confounding. So in order to quantify the relationship between the explanatory variables and the response, we need to address this issue. Finally, the last key challenge in this problem is to identify an optimal threshold for classification. The standard threshold in a logistic regression is p hat is equal to 0.5, where any observation with probability greater than 0.5 categorized to class 1 and 0 otherwise. But that may not always be ideal, especially in the case of imbalanced class settings. Further, in the case of multi-category classification, as we are exploring in this problem, the search for multiple optimal thresholds is key to obtain good classification results. So in this work, we propose a three-stage classification method for multi-type data. I will now present an overview of this method. So in the first step, or in the first stage, we tackle the issue of confounding. So we need to remove the effect of genomic variables and weather variables from the secondary traits. To do this, we use regression. We regress each of the traits on the set of weather variables and obtain the residuals U hat IP. Because the regression is high dimensional in nature, we use pinless regression techniques where the pinlization can be the lasso pinlization, adaptive lasso, ridge regression, or SCAD. Next, we regress each of these residuals, U hat IPs, on the set of genomic variables, again through the use of pinless regression techniques. And then we obtain the double residuals, so represented here by the U double hat IP. These double residuals represent the intrinsic effect of the secondary traits devoid of the embedded genomic and weather effects. In the second step, this is the main step of the process where we are building the classifier. We use logistic regression as the classifier of choice because of its simplicity and the ease of interpretation of relationships between the predictor and the response. One issue with the standard logistic regression in our context is that it does not allow us to enter the smaller dimensional data types before allowing the larger dimensional data types such as the genomic variables into the model. We need to do this to ensure that the model is not overwhelmed by the number of genomic variables without accounting for any information present in the other data types. So to counter this, we use a forward selection approach that will allow us to select the phenotypic variables first into the model, followed by the weather variables, and then followed last by the genomic variables. Using penalization helps reduce the number of variables in the model, and thus it helps improve the predictability of these models. In the third step, we look at threshold optimization. So let's consider an example. This is an example plot where we have X beta on the X-axis and the estimated probabilities in the Y-axis. Commonly, 0 is used as a threshold, but is it optimal in this case? Maybe not. So our method determines the best threshold to minimize the overall classification accuracy. So for this example, we found that a threshold of minus 1.7 was better than 0 at getting a lower classification error rate. Finally, we use the validation set to evaluate our model. We use the logistic regression coefficients that we obtained from step 2 and the optimal threshold that we obtained from step 3 to perform the classification. We evaluate the performance of the model using different criteria such as the overall prediction accuracy, the true positivity rate, and the true negativity rate. We're working on testing the model in different scenarios. So currently we're using a chickpea dataset that has 278 lines. The main trait of interest is a binary variable representing days to maturity. So the levels are either low or high. We have 6 additional secondary traits that were collected. The weather information was collected daily over the entire growing season for around 100 days. This yielded in 400 weather variables. And we had marker data, associated marker data with 10,000 markers. Our preliminary results show great promise. So we implemented the method in a simple balanced binary class setting with equal number of ones and zeros. And we showed that our method outperforms machine learning methods such as random forests and support vector machines. So our method achieved an error rate of 18%, as opposed to the 37% for the support vector machines and 44% for the random forests. So in conclusion, our method shows great promise in outperforming the machine learning methods. This is still a work in progress. So we're implementing the methods in various settings, such as binary imbalanced class setting and multi-class classification. We're also looking into methods to optimize the weather window. So the question is, do we really need all 100 days of weather information to predict our response? While we presented this method in an agronomic setting, we think that it's very applicable to any scenario where the objective is to combine data types of differing sizes. For example, we believe that it will be very useful in the area of precision medicine, where the main trait is the risk of a disease or reaction to medication. The secondary trait can be the other physiological measurements that were taken on the subjects of the patients. The medium dimension data can be the lifestyle and behavioral characteristics of the subjects collected. And finally, the high dimensional data type can be the genomic marker information itself. Thank you very much. If you have any questions, please feel free to email me at vamsimantana@gmail.com or through my website, vamsimantana.com. Thank you.